Factors that affect reaction rates. We're going to look at 6 things that will influence the reaction rates, where we can manipulate them to make the reaction go slower or make the reaction go faster. First of all, let's talk about the type of reactants or the nature of reactants. We can have molecular reactants or ionic. Let's first look at molecular reactants. For molecular reactants, I have molecules that are coming together. They need to come together and hit each other with the correct orientation and also the correct speed or the correct energy so that it's enough energy to start breaking bonds and make that activated complex. Because we have to break bonds, the speed for these reactions as compared to ionic is slow. So these are a lot slower compared to ionic reactions. A couple of factors affect that. A lot of it is the very, very high activation energy required to start those bonds breaking and making that activated complex. So for example, in this balanced molecular equation that I have right there, the methane, the CH4, and the oxygen, they have to hit the correct orientation with the correct energy in order for those bonds to break. And then each bond has to break and then be reformed. As a result, molecular reactions take longer to occur. Let's look at ionic reactions now. So we know molecular reactions are slow because bonds have to break. For ionic reactions, these are a lot quicker because they are all ready to react. When I take my lead nitrate and it says AQ, that AQ means aqueous. It means I took a solid and added it to water, and ionic compounds will break up. So this lead nitrate solid will break up into 3 ions. It will break up into a lead ion, a nitrate ion, and another nitrate ion. Now it's important that you put the charges on these ions so you can look them up or you can figure it out. So nitrate ion is a -1. I can look it up. And because I have 2 nitrate ions for every 1 lead ion, then I know that this is a +2 lead ion. Let's look at the next one. The next one we have potassium iodide. And the potassium splits up, and so I'll have a K and an I. It's important you put the charges. You can use your periodic table to help you. Potassium is in the alkali metal family, which they all have a +1 charge. And the iodine, is found in the halogen family. So it has a negative sign, a negative charge. And then let's look at what happens. So if I have a test tube of my lead nitrate that's dissolved and then my potassium iodide that's dissolved, when I combine them, I end up forming a solid. And the solid I form is lead iodide. And there's a little S right there to help you recognize that this is a precipitate that is formed. So this is the exciting part of the reaction. This is what happens when I put these together. I have all separate ions, and then as soon as my lead and my iodide collide, they stick together and they will make this solid. This is the leftover, the KNO3 is the leftover. This is the spectator ion, and it's actually in solution, not together. I still will have my K+ floating around and my NO3- floating around. So that's a little bit confusing where it's written together like this. So this is a total molecular equation, but this is not representing what the reaction is. If we want to represent what happened in the reaction, we are going to write what's called a net ionic equation. So for this, I'm going to look on the product side and look for a solid, liquid, or gas. And on the product side for this one, I have that solid. So again, this was the exciting part of the reaction. I made a precipitate. For the net ionic equation, again, it only includes the product that's a solid, liquid, or gas, and then whatever ions combine to make that. Well, I know that the lead had to combine with the iodide. And I need to make sure that I put the correct charges on them. This is important. So again, I already took you through how we know that's a +2 and how we know this is a -1. So I do need to balance this. So I do have a 2 right there, and so I'll put a 2 in front. So I'll have a lead ion and 2 iodide ions. As soon as they touch, they will combine and they will form this lead iodide. So again, ionic reactions are a lot quicker because I don't need to break bonds. They're all ready to go. Here is a activation energy that you can see that if you have a molecular reaction, it has quite a large activation energy in comparison to an ionic reaction. And so because the activation energy is so much less for ionic reactions, then they are quicker. Let's practice writing some more net ionic equations just to make sure that you can do this. So again, you're going to look on the product side and look for a solid, liquid, or gas that has formed. And here I see a solid has formed. So I'm going to just pull that down. And I can put the S or not. That's not important. So I know that this are going to be my spectators. Those are the ones that did not participate in the reaction. It's kind of like they're the leftovers. So I want to get rid of the sodium and the nitrate and then just write what's left over. So I know that a silver has to come together and with a chloride ion to get the silver chloride solid. I need to put the charges on them. So looking at silver, silver can only be a +1. You can look it up. It's the only oxidation number it can have. I also can play detective, and I can see that there's an NO3 group there, and I know it's a -1, and so that means that the silver must be a +1 because it's put together with a 1:1 ratio. And then let's look at our chlorine. Chlorine is a halogen, and halogens we know are -1. I also could look at what it's put with, and it's put with a sodium, and a sodium is a +1 because it's an alkali metal, and my halogen or my chlorine is a -1 to cancel that out. This is my balanced equation. So I know an Ag and a Cl come together to make AgCl, and I've written my charges. And one thing that you'll see with these net ionic equations is the charge on each side will be equal to each other. So not only can you count for atom, but you can look at the charge and that they should be the same. So one silver on each side, one chlorine on each side, and my charge is 0 on each side. Let's look at the next one. So my exciting part is that solid right there. So I'm just going to bring that down, and then I'm going to look and see what comes together. I see that the CO3 is a polyatomic ion because it's together on the left-hand side and also together on the right-hand side. Looking on a periodic table, calcium is a +2. It's an alkaline earth metal. And I can look up the charge of the polyatomic ion, and it's a -2. Or I can think if calcium's a +2 and I put it together with a 1:1 ratio on the product side, then it better be a -2. Okay. And let's do one more. So the exciting part of the products, there's my solid. So I'm just going to bring that down. And then I'm going to put my ions together. I need to include the charges. So looking up copper, I find that copper can be a +1 or a +2. And I see that I have 2 chlorines here. They're both a -1. So that means the copper must be a +2 to cancel out those 2 chlorines. So this is a +2. And then OH is a polyatomic ion with a charge of -1. So in your packet, you should have some net ionic equations. They may not be questions 18 to 21. They may be off a little bit, but go ahead and take a try at doing these net ionic equations. All right, let's come to our second way to manipulate the rate of reaction. So number 1 was whether it's molecular or ionic, and ionic is faster. Number 2 is concentration of reactants. So if I have a dilute or very low molarity versus a concentrated or high molarity of reactants, that is going to influence how fast it goes. The more concentrated it is, then the faster it will be. So more reactants mean more collisions if enough energy is present, and because of that, it's colliding more, it's going to react faster. So if you increase the concentration, you will increase that rate. And again, this is due to more collisions. And you're going to find that these rates are dependent on the collisions. So if you get more collisions, it will be faster. If you get less collisions, it will be slower. Temperature, high temperature versus low temperature. A high temperature, the molecules are going to be moving faster and they're going to hit each other harder. And so I'm going to have an increased reaction rate with the temperature being high. And temperature is one of those things that has 2 reasons why it makes the reaction rate faster. And again, it's because of the number of collisions and the force of collisions. The reason why we put our groceries in the refrigerator is to retard spoilage. So if we had some meat or some dairy products and we just left it out on the counter, it would quickly rot. And that is because of the temperature. So the temperature will be warmer on the counter, and so the rate of rot will increase. But if you put it in the refrigerator, it's at a lower temperature, so it will slow the rate so that we'll have some time to eat it before it spoils. At the bottom, I have a chart here showing a diagram of distribution of two different temperatures. So remember, even though I can take the temperature of a sample, that doesn't mean that all those molecules are moving the same speed. I'm going to have some that move a little bit fast, some move a little bit slow, but you can see with the higher temperature, more molecules are going to be moving faster as compared to the lower temperature one. And then I have my activation energy indicated there. And so in order to react, those molecules would have to be going faster than that activation energy that was required. And so you see with the higher temperature, more molecules can react. With your low temperature, just a very, very small portion can react. And so you can see that even though you put your food in the fridge, you're still going to have some food that spoils quicker because the molecules in the food might have enough activation energy to start that spoiling process. Pressure. Let's compare low pressure to high pressure, and this applies only to gases. So I have two containers here. This is a very low pressure and a high volume. So notice they are opposite. This one here is a very high pressure and a very low volume. So we can see as you put something under pressure, then the volume will decrease. Which one is going to react faster? Well, when you change the pressure, you're changing the volume, and that changes the concentration. So this just goes back to the concentration. If you have a high concentration, it's going to go faster because you have more collisions. And again, this applies only to gases. Surface area. So this is for just solids because gases don't have a surface area. Let's compare a low to a high surface area. How do we get a high surface area? We can crush it, pulverize it, put it in smaller pieces. And we find that if you have a high surface area, there's more area for reactants to be in contact. The small pieces here, the little red reactant can get to more of the green molecules. If you have a solid crystal, you can see that the red can only react with the ones on the edges. So those ones in the middle are protected, so to speak. By crushing something, it makes it react faster. All right, our last thing to influence reaction rate is adding a catalyst. So what a catalyst does is speed up a reaction by lowering the activation energy. I have quite a high activation energy in this graph, and you can see that if I add a catalyst, that activation energy will become lower. So the catalyst can take the reactants through a different pathway, through some different reactions, but I still get the same product. So if you add a catalyst, you will see it at the beginning of the reaction, but then you'll also see it at the end. So it will get spat out of the reactions. So it can be used again. So this is very desirable in manufacturing. If they're making some sort of product, very, very oftentimes they'll use a catalyst because time is money. And if you add a catalyst, once you purchase it and put it into use once, you can just keep using it. Just keep adding more and more reactants to it. Because again, a catalyst is not used up. Catalysts can help the molecules line up correctly, or again, they can have an alternate pathway to make the same product. What do catalysts have to do with equilibrium? Really nothing. All a catalyst does with an equilibrium reaction is get it to equilibrium faster. So you can see with the first diagram, I'm at equilibrium here. And the second diagram, I'm at equilibrium here. So a lot faster. So a catalyst scoot over that equilibrium point. Here is a Maxwell-Boltzmann distribution, and we can put our activation energy, I'll make it larger. So this is just normal reaction. If you add a catalyst, you will scoot that activation energy over. So again, this is with the catalyst and this one is without. So you can see that a lot more molecules can react with that catalyst because the activation energy lowers. There are two types of catalysts. The first is called a homogeneous catalyst. And we have a reaction right there at the top, a decomposition of hydrogen peroxide. This is a very slow reaction because it is a molecular reaction. I have to break bonds, I have to make bonds. It's quite slow. So if you have a really, really old bottle of hydrogen peroxide underneath your bathroom sink, if it's like 10 years old, chances are it's all water. The lid of the hydrogen peroxide that you get at the grocery store is very special because it allows the oxygen that forms to escape out the lid. So that way the bottle doesn't blow up as the oxygen is made. Down here I have an alternate pathway for my catalyst. You can see the catalyst because it's at the end and it's at the beginning. So this is the catalyst added to hydrogen peroxide, and what happens, that iodide ion will take it and form an intermediate right there, the IO. So I've broken down one hydrogen peroxide molecule, and then the IO goes through a second reaction and breaks down yet another molecule of hydrogen peroxide. But then at the end, I do have all the hydrogen peroxide used up. If I were to add these two equations up, I would get this total reaction. By canceling out any intermediates and the catalyst that's at the end and at the beginning. So I get the same overall reaction, but it just happens faster because the catalyst will lower that activation energy by taking it through a different pathway of reactions. I forgot to mention these are homogeneous catalysts because they're at the same phase. Do you see how the catalyst is aqueous and the hydrogen peroxide is also dissolved in water? And so because it's at the same phase, we call it a homogeneous catalyst. Other catalysts are in different phases. Very common, we will have a solid catalyst and then we'll have the gaseous reactants. So because they're in different phases, solid and gas, then that's known as a heterogeneous catalyst. These catalysts are a little bit different. They provide a active site or a site that, or a place that the molecules can sit down and they can line up. So for example, I might have on my solid certain shape like this, and if I have a gas that will fit that shape, and then I have another gas come in that'll fit the other shape, when they sit down, they are able to react right here. And so then they'll make a molecule. So here's an example here. So in your catalytic converter in your car, burning fossil fuels can make some really bad gases. One of them is carbon monoxide, which is very poisonous. So what your catalytic converter does is take oxygen and carbon monoxide and it combines it to form carbon dioxide. So not poisonous to humans and animals, but probably poisonous to our planet because it's a greenhouse gas. Here's another picture of a catalytic converter that you can see that not only does it get rid of that CO2, but it also gets rid of some of these nitrous oxides that are poisonous to us, and it turns it into just atmospheric nitrogen and oxygen. It's not just a flat piece of metal. You can kind of see it here. It has lots of surface area, so there's lots of places for these bad gases to react with each other. So they will line up, and because they're lined up correctly, that orientation is just as it should be. And so very quickly it can react to form carbon dioxide, nitrogen gas, and oxygen gas, and some water vapor. An enzyme is a biological catalyst. So if you look at the enzymes in your body, we don't call them catalysts, we call them enzymes, but really it does the same thing. Here's a picture of this lock and key. This is how our food is digested. So that enzyme will target certain larger molecules and it will split it apart. This happens in your mouth. So your saliva contains an enzyme called amylase, and that amylase attacks starches. So if you eat a piece of bread or a cracker and you chew it up, and if you actually keep it in your mouth long enough, it will start to taste sweet. And that's because your amylase is doing its job. It's cutting it up into these simple sugars